So we're trying to find examples of groups, and we'd like to consider groups of matrices. So I'm going to let M2 of R be the set of matrices which have their components. So I'll write my matrix A, B, C, D with A, B, C, and D in the real numbers. And so what we'll say here, and we want this with matrix multiplication as the operation, as the group operation. And so this matrix multiplication will satisfy associativity. I'm not going to show this, but it's not too hard to do. You can try it on your own. There's also an identity. If we think about the identity matrix, we'll see that the identity matrix satisfies this axiom. For all matrices, we'll call it A, M2 of R, I times A equals A. So this is good. We have that. But we don't have our inverse axiom. So we won't actually be able to say that M2R is a group. It's going to not be a group. And just as an example, we can think about the matrix with 1 in this top right component and zeros everywhere else. If this were to have an inverse, it would be, we would have to have something like this, where we have this matrix right here times another matrix, and it would have to be the identity right here. And we can actually do out these equations here. We would have, let's see, if I multiply this row or this column by that row, I'll get C equals 1. C, A times 0 plus C equals 1. The bottom row gives me nothing. And then we'll have this top left component will be that D equals 0. And then if I multiply this by this, I'll get B times 0 plus D times 0 equals 1, which gives me the equation 0 equals 1. This is bad. And this is why this matrix right here doesn't have an inverse. This is just a proof, I guess, that this matrix doesn't have an inverse. So one strategy that we employ a lot in mathematics when we have a larger set, like this set of 2 by 2 matrices here, we can restrict our matrices to only the ones which have inverses. So some matrices have inverses, and those matrices are precisely the ones with, for example, non-zero determinant, or they have linearly independent columns, for example, or rows. And so the mathematical name that we use to describe this is GLN, and then we have R here. So this is the set of 2 by 2 matrices such that A, B, C, D is invertible. And of course, A, B, C, and D are in R. And of course, this is a subset of M2 of R. It looks like I put an N over here. Really, this should be a 2. I can define it just the same way, just analogously for any N. And so I guess the last point that I would like to make, so GLN is actually going to be a group. GLN will satisfy the inverses, and the way you find the inverse is you take the inverse matrix, like we know how to do from linear algebra. So the last thing I'd like to show is that this GLN group, or GL2 at least, is not commutative. in that it is not abelian. So here's an example. I'll take matrices 1, 1, 1, 0 and 1, 1, 1, 0 with the 0 in these two different components here. And I will multiply them two ways. First with the like this, with the top hand 0 on the second one, and then the second time we'll multiply it like this with that same matrix coming in the front. And what we'll see is we should see here, if we multiply, we'll get 2, just read off 1, this will be a 1, and then what will that last will be? It'll be 1. But if we go down here to this matrix and start from here, we'll get 1 times 1 is 1. So we've already got a component that doesn't match. That'll be 1. This top one will be a 1, and the last component will be a 2. So we have matrices here, and all of these are invertible. If you want, I can check their determinants. This is 1, determinant 1 minus 0 is equal to 1. This one also has determinant 1. If I say 2 times 1 minus 1 times 1, this will also be determinant 1, right? So all of these are in GL2 of R, right? So is this GL2 of R, right? But they don't commute. So what I've just proven, and what this implies, is that GL2 of R is not an abelian group.